So I'll do two examples. Find dy dx for tangent of xy is 2x plus y, and then find an equation of the tangent line to this given curve at that point. If you want to try these on your own, just press pause and then press play when you want to see the answers. Okay, so here's the first one. So we start off with tangent of xy is 2x plus y. This equation, I certainly don't know if it's possible to solve that for y. I don't think it is, because you have trig functions and you have a polynomial expression. It's usually hard to solve any equation when there's more than one type of function involved. So it's doubtful that you can actually solve this explicitly as a function of x. But we don't need to. We just differentiate implicitly. So first, tangent of xy. That differentiates to secant squared xy. And then times the derivative of whatever is inside there, chain rule. X times y needs a product rule, right? Because we have x times y. So it's the derivative of x times y, 1 times y, plus x times the derivative of y, which is 1 dy dx. So that's our left side's derivative. The right side, 2x differentiates to 2, y goes to 1 dy dx. So again, the left side needed the chain rule and the product rule. Tangent differentiates goes to secant squared, and then x times y is a product. So it's the derivative of x times y plus x times the derivative of y. And then we solve for a dy dx. We have to multiply out the left side of our expression. So y secant squared xy plus x secant squared xy dy dx. When you have all those terms being multiplied, you put polynomial terms in front, trig functions come after it. Dy dx, differential terms always go last. So that's like the order that you would usually see these in. We combine our dy dx terms on the same side. So I'm going to put those on the left side of the equation, and I'll move everything else to the right side. Right, so I move this to the left side. And we factor out the dy dx because we want to solve for it. And again, dy dx terms always go last. So when I factor it out, it goes to the end of the expression. Just looks better that way. And last step, divide by whatever's in front of dy dx. Dy dx is 2 minus y secant squared xy x secant squared xy minus 1. That is the derivative of y with respect to x. So that's the answer to the first problem. And yours might look differently if you solve this in a different way. If you move the dy dx terms to the right side, it would just be like the opposite. You'd have that minus 2 over that minus the secant squared term. Right? Because when you solve equations differently, the answer is just a little bit different. Let's solve the second one now. The equation, the tangent line of this curve right here. So for the tangent line equation, we need the x and y point, which we have, and we need the slope, which is dy dx. So we already have this part. Y is the y value plus the slope, x minus the x value. All we need is the slope, which is the derivative at the point 3/2 comma 3/2. So we find dy dx. So x cubed differentiates to 3x squared. Y cubed is 3y squared dy dx. 3xy is the product rule, 3x times y. So it's 3 times y plus 3x times dy dx. Then we'll solve this for dy dx. I can also divide everything by 3. That's cool. All these 3's cancel out because each term has a 3. Put my dy dx terms on the left side. I could have put them on the right. I just chose this side. and then factor out a dy dx, and divide by whatever's in front of dy dx. So dy dx is y minus x squared over y squared minus x. So that's my derivative. It's in terms of two variables, so I plug in both 3/2 for x and 3/2 for y. Doing that gives me 3/2 minus 3/2 squared over 3/2 squared minus 3/2. Simplify that whole mess up, and it gives you -1. And so, my tangent line is y equals the y value plus the slope, x minus the x value. And if you're a fan of simplifying equations, you can simplify this, of course. 3/2 plus 3/2, which is just 3. That's kind of cool. Either one is totally fine, though. I would keep it as that, actually, just because it's easier to do less work. And there you go. One quick historical side note, I can't avoid doing those. This kind of function is what graphs were made to do. When René Descartes came up with his idea of the graph, of making an equation turn into a picture, when he invented this concept, although there may have been others that did it first. But it was for equations like this. In fact, I'm pretty sure it might have been this equation called the Folium of Descartes, which was like one of the first graphs ever made. And it makes sense why the first graphs were for kind of harder equations. He needed a more advanced way to analyze these equations. So he figured out how to graph an equation, how to see the geometric approach for an algebraic expression. Okay, but anyways, the important part is the implicit differentiation. Don't forget that y is always a function of x, and so whenever you differentiate it, multiply by dy dx. Okay, and workshop, you'll have more examples of this.